Go for it.
Hi, today we're going to be talking to you about hydrogel bead development for microbial culture encapsulation. Presented to you by Alyssa, Margaret, Tegan, Annalise, Willow, and myself, Connor. And we are mentored by Dr. Skip Rochfort and Dr. Louis Semprini from the School of Chemical, Biological, and Environmental Engineering. So a widespread issue throughout the US is groundwater contamination from volatile organic compounds known as VOCs and co-contaminants such as 1,4-dioxane. In low permeability zones in the subsurface, common remediation techniques such as pump and treat are not sustainable. A bacteria strain, Rhodococcus rhodochrose, ATCC 21198, is an alkane oxidizing bacterium capable of degrading some VOCs and 1,4-dioxane. So our proposal is to create permeable reactive barriers with the Rhodococcus rhodochrose bacteria co-encapsulated by hydrogel beads to biodegrade contaminants occurring in the groundwater aquifers, as shown on the figure on the right.
So hydrogels are made by cross-linking polymer chains, and this can be done in two different ways, chemical or physical. Chemical cross-linking is cross-linking using covalent bonds, and this cannot be undone. But physical cross-linking is cross-linking using any other method other than covalent bonds, and this can be reversed. For example, gelling gum is a thermogel, so it will cross-link when it's heated or cooled to specific temperatures, but within a certain range, it will be a solution, and so it uses physical cross-linking. What we are doing in the lab is making beads, and to do this, the polymer solution is going to be dropped into the cross-linking agent using a pipette. When this happens, the outside of the bead will cross-link first and form the bead shape. And as you can see in the diagram, the sodium alginate solution would be dropped into the calcium chloride solution, and as the calcium ions penetrate the bead, they cross-link the sodium alginate, but the calcium ions won't go deeper into the bead until the alginate towards the outside has been almost completely cross-linked. And so you can see that this forms a ring of gel with the rest of the solution still contained inside. Once the calcium ions reach the center of the bead, then that bead is considered fully gelled and it's ready to be removed from the cross-linking agent. The polymers that we have been exploring are sodium alginate, which we use for its nice round structure, low acyl gelling gum, which we use for stability, and they make very firm beads, which is what we're looking for. We're also using PVA for its strength and its durability. It has a long degradation time, and chitosan because it contains antimicrobial properties. The purpose of our work is to encapsulate the rhodococcus into hydrogel beads to degrade contaminants such as 1,4-dioxane, which is carcinogenic, in order to treat the groundwater. So in the short term, we've been looking to create beads that are both durable and able to provide an environment for the rhodococcus. But longer term, we're looking for the best method for encapsulating these microorganisms into the hydrogel beads, and then the best method for scaling up our entire production process.
In order to begin the bead making process, we needed to make the different types of polymer solutions for our bead creation. And the 4 types of polymers we used were polyvinyl alcohol, or PVA, chitosan, low acyl gelling gum, and sodium alginate. The basic process for solution making for the PVA, chitosan, and low acyl gelling gum is to measure the desired amount of water into a beaker, which is located on a magnetic stir plate with a magnetic stir bar. Then the water is heated to the necessary temperature for each polymer, and the polymer is slowly incorporated into the water. For the sodium alginate, the water and polymer are blended together using an electric mixer. However, by themselves, these solutions would not form gel beads, so cross-linking solutions also had to be made. The cross-linking solutions were borax, calcium chloride, calcium lactate, sulfuric acid, and thermal, which is temperature-based. And many of these solutions were created in a very similar way to the polymer solutions by slowly adding cross-linker into water that is continuously mixed. When working, we also tested different solution mixes, and these mixes were made by combining the individual solutions together on a magnetic stir plate with the desired weight by volume of each. And as previously mentioned, the bead creation process was created by taking the polymer solution and using a pipette to drop that solution into the cross-linking. solution, and gelation was observed. And then the polymer was left into that solution until total gelation had been reached. And when a successful solution had been identified, this process was taken even further through the performance of time trials. Time trials are dropping many beads at once into the cross-linking solution and then taking them out at different time intervals to test their properties and observe how they've changed. And what we were looking for was for them to become firm and strong beads. And then these were the concentrations of the different solutions that we made and the temperatures that they were heated to achieve full incorporation. For the PVA, we tested using 2, 4, and 8 weight % solutions and heated them to 90 degrees Celsius. For the chitosan, we created a 2 weight % solution and heated it to 80 degrees Celsius. For low acyl gel and gum, we created a 1 and 2.5 weight % solution, heating that to 60 degrees Celsius. And finally, sodium alginate, we made a 0.5 to 2 weight % solution and did that at 25 degrees Celsius. And these are all individual solutions, which we tested, but we also tested the mixtures, which were created by mixing the solutions together and used for further analysis and testing.
First, we started with testing PVA beads, but unfortunately they form very thick and structureless beads that aren't really ideal for our project. And then we did a bunch of research to determine 4 different polymers to work with and combined them in different ways to find an ideal bead. Chitosan on its own does not cross-link for thermally or with sulfuric acid, so that was not going to work. And then we tested low acyl gel and gum and chitosan, and that formed a bead, but it didn't have all of the properties that we wanted. The sodium alginate, PVA, low acyl gel and gum, and chitosan beads, when combined, they gelled together before adding any cross-links, so it was unable to bead in our solution in the way we wanted. The beads that we were successful in making were sodium alginate, PVA, and low acyl gel and gum. These beads, when cross-linked in cold calcium chloride, created round, very strong beads, and they gelled in 14 minutes.
So in conclusion, because of all the research that she just presented, we'll be moving forward with the sodium alginate, PVA, and low acyl gel and gum polymer solutions with the cold calcium chloride and the cold sodium lactate as the cross-linking agents. We plan to introduce the microorganisms to the hydrogel beads by incorporating their solution with the polymer solution, and we will be testing for growth, degradation, and stability. Growth will be monitored and recorded through isobutane uptake tests using a batch reactor, and degradation will be tested using a pilot scale bioreactor to emulate a groundwater aquifer. As mentioned before, we're also looking into mass production of the hydrogel beads containing the microorganisms, and a possible option could be to use a coaxial capillary extrusion gel bead generator, which we have available in our polymers lab. The system is flexible, so we will be able to make alterations that align with our research. And it can produce 100 beads per minute or more, depending on the size. So this seems like a great option moving forward. You can see an example of one to the right of the words.
And last, thank you so much for taking the time to visit our project page and learn more about our project from Connor, Alyssa, Margaret, Willow, Annalise, Tegan, and our mentors, Dr. Skip and Dr. Lewis Semprini. We thank you and wish you well.